But first thing I want to talk about is cosine 2x equals 3 sine x minus 1. A couple things that are an issue here is that obviously the cosine and the sine, right? We don't like having those together if it's avoidable. We like to replace one with the other. But the other issue at hand is that there's a 2x and a 1x. And I think the 2x and a 1x is actually the main concern, okay? And if we can fix that, at least in this case, it automatically fixes the issue with the cosine and the sine if we're intelligent about it. We kind of, may talk about this in Algebra 1, Algebra 2, College Algebra, and you see that, throughout those 3 courses, we deal with a lot of different styles of equations, right? But there is absolutely no way that we can talk about every single equation that you'd ever come across because there's an infinite number of them, right? In every kind of category. Infinite number of linear equations, infinite number of quadratic equations, infinite number of cubic equations, infinite number of logarithmic, that kind of stuff, okay? So what we do is we try to build a kind of systematic set of processes that you can kind of piece together and use together to address equations that might be different than the last one you solved. Does that make sense? So trying to learn these individual components to when we get to an equation that we've never seen, and we've never seen the components or the parts being related the way they are, maybe we can still break apart and use maybe 2 or 3 processes that we've learned that will address certain situations. Does that make sense? So that's kind of maybe what we're doing here. I look at this first and I say, okay, cosine 2x. I just think it's kind of silly that they wrote the right-hand side this way. We're going to distribute that 3 through, right? Okay. So now I got a sine x and cosine 2x. I don't like that. I don't like the 2x and I don't like the 1x. Okay, and we always have to address that. You can't solve these equations if you've got a 1x and a 2x, or a 1x and a 3x, or a 3x and a 4x. You can't address them if they're different. So you have to work through changing them, okay? And really, the way that you work through changing, and we'll see this at the end, is that you take 2x and you rewrite that as 1x plus 1x, right? Does that make sense? But we know that there's a better formula at the moment than that, okay? This is a cosine double angle, right? So cosine double angle, and tomorrow you'll have this sheet. Could be cosine squared x minus sine squared x. It could be 2 cosine squared x minus 1, or we're going to rewrite it as 1 minus 2 sine squared x. All of those take our double angle and kind of degenerate it down to 1x, if that's a word. Okay? And that's what we want, right? Now, which one of those is more beneficial for us because of that term there? Which one of these 3 would you probably want to use? The bottom one. Okay? You want to get those terms to be the same. And that's one of those relationships that we want to use and think about when we're solving maybe another trig equation that we haven't seen before, okay? or seen similar questions before like that. Always try to get, if it's possible, and that's not always going to be possible, so you might have to use or go down some other avenue, but if you can, try to get all your trig ratios to be the same one, okay? And like I said, these all, if you remember cosine double angle, all these formulas here stem from the fact that cosine of 2x is actually cosine of x plus x, and that turns into, cosine of x minus sine of x, right? And then through some substitutions, these things degenerate. But now if we do this, make that substitution, 1 minus 2 sine squared x is equal to 3 sine x minus 3, okay? Now we see powers of 2, we see powers of 1, so when that happens, what do you think we should try to do? If you have powers of 2 and powers of 1. I gave you something like 1 minus 2x squared equals 3x minus 3. What would you do if I told you to solve for x there? Exactly. And because your thought is to do what process? Why do you move them to one side and set them equal to 0? So you can factor. Okay. So when we see those things, and generally speaking, guys, it's when you have degrees greater than 1, that's probably the approach that you're going to try to do, is try to factor. And we know we haven't seen too many of them with, cubed or the 4th power, 5th power, but we have all of those polynomial techniques of factoring that we can actually kind of use inside these trigonometric equations. So I'm going to move everything to one side. So it's going to give me 0. Ends up giving me, what, positive 2 sine squared x plus 3 sine x minus 4. Okay. And things have now just cleaned up quite a bit, right? All right. What would you do if you're trying to factor this? What would your first approach maybe be, or first thought? A times C method, right? And even before that, you probably look at this. Does everything divide by 2? And the 3 doesn't, so that's out the window. So you do A times C, and we get negative 8. Any numbers that you know off the top of your head that multiply together give me negative 8, but have to give me 3? Nope. So A times C method does not work. Okay? And that tells me then if the A times C method doesn't work, I have ultimately one other option, quadratic formula. Okay? Quadratic formula opposite B, plus or minus B squared minus 4AC all over 2A. Okay? And remember, when we used that in algebra, it was always equal to our variable part, right? Which in algebra usually that was x. Okay? But what is our variable part right now? Sine of x. Okay? That's what we're trying to solve for here when we do this. And that's the one thing that people get stuck with. And I think it's, maybe due to our habits of just in algebra 1, we just write that down. And we don't remember that it's equal to something. Okay? So right now we're solving for sine of x. And if you're a person that uses the u substitution, maybe you got like 2u squared plus 3u minus 4 here, which is an approach that we've talked about. This would be u then, correct? But we probably said at some point that u was sine of x. Now plugging in those components, it's just the coefficients now. So you get negative 3 plus or minus. It becomes 3 squared minus 4ac all over 2a. And I get that. And that's what sine of x is equal to. Okay? Now, just going back to our algebra concepts, that validates to me that number at 41, since it's prime. Okay? And even if it's just essentially a number that's not a perfect square, tells me that the A times C method definitely would not work, or any other kind of shortcut technique like that. This is the only thing that would work. Okay, so here's the question. Okay, sine of x. So if I take, this radical 41, let's say it's a little bit bigger than 6, right? Radical 36 would be 6. What's negative 3 plus 6? 3 divided by 4 is what kind of number? Is it positive or negative? Positive. So if I do the negative 3 plus root 41, this is going to be a positive number, right? And what two quadrants is sine positive? First and second. So when I use my calculator here, my calculator is only going to give me the first quadrant solution. I got to do some work to find a second quadrant solution. Okay? If I do negative 3 minus root 41, what's negative 3 minus 6? Negative 9, right? What's negative 9 divided by 4? Negative 2 and a fourth, right? Does the sign ever get to negative 2? No. Okay? So, and then we'll do the math here again, but that should show that that's an undefined solution for the negative values there. Okay? All right, so let's try to solve for x. So if I want to solve for x, I got to use the inverse sign, right? Okay, so the inverse sign, let's bring up a calculator here real quick. All right, so, and I'm going to do this in radians. So inverse sign of negative 3 plus square root 41 well, all over 4, right? Gives me 1.017 radians. Okay, so that means that if I'm looking at the unit circle, okay, this number in here, if I were to actually evaluate that, I think it's like 0.85 or something like that. It's saying that when my y value, I don't know what my x is, but when my y value is negative 3 plus radical 41 all over 4, the angle that we're talking about that gets me there, okay, that angle right there is 1.017 radians. Does that make sense? Okay. Isn't there also, because of the symmetry, an angle right there that would be the same y value? Okay. So then, how do I find that one? Well, I know that's pi, right? Okay. Can I take pi and remove from it that blue angle? And isn't that blue angle the same thing as that angle? Okay, so I can take pi and subtract from it 1.017, 469. I get 2.124. Okay, so my two values right now are x equals 1.017 radians and x equals 2.124 radians. If you're a person that says that confuses me, okay, feel free to do it in degrees. Okay, so if I do this in degrees, then this would be 180 minus 58.9, or 2967. It's 121 degrees. Okay, and just to prove that that is right, 121.7033. If I multiply that by pi divided by 180, does that give me my 2.124? Okay, so if you like to do things in degrees, if that makes more sense to you, by all means do that. But then make sure how the question is phrased. If it says find solutions between 0 and 2 pi, then they're looking for radian solutions. Okay, if it says 0 to 360, then fine, use the degree mode. All right, so how does that work then for when this number here becomes negative? Okay, and the reason that's undefined is because that quantity is negative 2.35. And what we're asking then, okay, remember, that would have been sine of x is equal to negative 2.35 is what we'd be asking before we do the arcsine function. We'd be saying, when does that curve reach negative 2.35? And it never does, right? Okay, So that's why these solutions, when we go arc sine or sine inverse, is undefined. Okay. If it did, because sometimes you will get a solution that is defined. You know, if this number here was like 21, let's see what that would give me. Undefined still. Let's go 1. Well, at some point, you may be able to find a solution that is still between -1 and 1. So you'd have 2 more solutions that come from that. Does that make sense? And they would, because they're negative, they would exist in the 3rd or 4th quadrants, because that's where the sign is negative. And you would just go through that unit circle kind of process to decipher what those values are between 0 and 2 pi. But I think that question is good to think about and look at for the mere fact that we haven't dealt too much with using the quadratic equation, or sorry, quadratic formula to address these solutions. Okay. Again, you know, if I want to maybe before the question or maybe after the question say, okay, what is this going to look like? I think it was a sine of x minus 1, the original equation. All right, so those are my 2 curves. If I just click on them and look at the intersection, 1.017, 2.124. And those were the solutions that we found by hand, right? Okay. Desmos generates that pretty quickly for you. All right, let's do we'll come back to that one. Let's do this one. You know, we like questions that have a 1x as the argument, but sometimes it's unavoidable in regards to keeping it a 1x. Okay? For the fact when we look at this one, we might think, oh, let's factor. Okay? Because we've got a bunch of products number on the left. We've got 3 numbers on the left, we multiply together. They equal radical 3. Okay? And we've talked about this quite a bit in algebra. But if I, leave it this way, this has to be a 0 for me to factor, right? And the logic of that is because if I have, let's just use variables x and y. If I say x times y is equal to 0, you know that whatever that number is, if that number is non-zero, that one has to be 0, right? Or if this one is non-zero, the x has to be 0. But if I were to say, just to make it kind of prove my point here, instead of using radical 3, what if I said, like, x times y is equal to 24? Could I say then that, well, x could be 1, right? What could y be? 24. What if x was 2, what would y be? 12. If x was 3, what would y be? 8. If x was 4, what would y be? A lot of different answers, right? Okay, now you might say, well, we'll run out of answers at some point. No, we won't. Okay? Because what if x is, 1/4? Then y would be 96, wouldn't it? Or vice versa, x could be 96 and y be 1/4. If x is 1/5, okay, we can figure out what y would be. Does that make sense? So we can't kind of narrow in on those values for x and y individually when their product is equal to something other than 0. Okay? So when it's radical 3, we can't just start factoring. And some people will say, well, I understand that, but what if we move this radical 3 over and we get a 0 over here? Well, then we still have a product and then minus radical 3. So we still be asked, okay, what do these 3 things multiply together to give me radical 3? so that I can subtract radical 3 from it to get 0. Does that make sense? And still an infinite number of things that can do that. So not the best thing here, not the greatest situation. But as you guys start seeing more and more equations that deal with the trig ratios, hopefully that becomes an expression that opens your eyes. Okay? Because that thing right there is part of this identity. Remember seeing 2 sine x cosine x before? Does anybody remember what that identity is? Good, that's sine of 2x. Okay. So, would you guys agree that this over here, because we can't make a direct substitution yet because it's 4 sine x cosine x, not 2 sine x cosine x. Would you guys agree that 4 is the same thing as 2 times 2? All right, this way. Now, is that thing, which we can now substitute as that thing, right? So now we get 2 sine of 2x. What's nice about that? We got rid of the different functions, right? The varying functions. I can now divide by 2. So sine of 2x is equal to root 3 over 2. And like I said at the beginning, sometimes that 2x or 3x or 4x is unavoidable. We made a substitution here that is unavoidable. It increased those 1x's to 2x, but that's fine because now it sets the problem up so we can use what we talked about yesterday. Yesterday we talked about multiple angles, right? Okay, so we're gonna solve it. Where is the sine function equal to root 3 over 2? Pi over 3. And 2 pi over 3, right? Okay. Now, what did we just solve for? What should I put right here? Careful. 2x. We just solved for that 2x argument, okay? Because if we make the direct, so right now we're saying 2x is equal to pi over 3. If we make that substitution right here, 2x is pi over 3. Is that a true statement? The sine of pi over 3 equals radical 3 over 2. Yes, okay? So that has to be the 2x over there. So yesterday we said when we do this is that multiple angle concept, okay? You solve for the sine function, just like normal, but then we're going to start adding to this 2 pi k and 2 pi k. So this is going to address then that situation of kind of moving around your unit circle multiple times, or if we think about it looking at the periodic function, it's the fact that the 2x actually compresses the curve, and you're going to get more solutions inside your initial interval. So this takes care of finding those. So once we set that up, we then go through and solve for x, right? So that's going to imply that x equals, multiply everything by a half, pi over 6, bless you. And then plus pi k. And this bottom one is going to imply that x is equal to, multiply by a half again, so pi over 3. Plus pi k. And those then start giving us some of our solutions, but not all of them. It's not all of our solutions between 0 and 2 pi. We have to then say, well, what are our kind of rules for k? K has to be integers that start at 0 and go up to n minus 1, where the 2, that's our n right there, okay? Whatever number is in your argument is your n. So k always starts at 0 and goes up to n minus 1. So 0 and 1, right? Okay. And we'll do the same thing here. K is equal to 0 and 1. So if k equals 0, then this thing here is just pi over 6, right? If k is equal to 1, this thing here is pi over 6 plus pi, becomes 7 pi over 6. Doing the same thing down here. When k is 0, we get pi over 3. And if k is 1, we get pi over 3 plus pi, which is 4 pi over 3. Those are your 4 initial solutions between 0 and 2 pi. If I wanted the infinite number of solutions, we would just add 2 pi k to all of those, where k again is an integer. Okay. So again, processes that we went through. Identity substitution there, right? Multiple angle process there, correct? Okay. This was an equation that we'd never seen before. But to address it, we use a grouping of processes that we have addressed before. Okay. And to get really good at this, it takes practice, guys. It takes seeing as many of these things as we can. Okay. Looking at that thing then for graphically for sine of x, cosine of x, and y equals square root of 3. Okay. Again, this question here is going to be really nice on Desmos because it gives me the pi over 6. It gives me the pi over 3. It gives me 7 pi over 6. It gives me 4 pi over 3, right? Okay. But if you're going to use this tomorrow, 100% fine. You need some version of this work to validate that. Okay. You know, if you've got all this, obviously 100% give you full credit. But if you just have that stuff, you go straight from here to there, I'm not giving you credit. I need to see that work that I deleted. Okay. All right, so this one is the same thing. It's the exact same thing, but what is different here? Maybe you write this way. That multiple is now a fractional multiple, right? Okay. So it's a fraction between 0 and 1. And if a multiple, like a number like 2 or 3 or 4, kind of compressed your periodic curve and gave you more solutions inside your interval, when we go between 0 and 1, what's that going to do to your periodic curve? It's going to stretch it. It's going to pull apart, right? So when it pulls apart, that means some of your initial solutions are actually leaving your initial interval. Does that make sense? They're going outside of it. So here with and this is a half angle situation. It could be 1/3, it could be 1/4, it could be whatever fraction it wants to be. We're going to lose answers. We're gonna, initially, if I think I have 2 answers, maybe I only end up with 1. Or if I have 4 answers, maybe I only end up with 2. Sometimes I'll have 2 answers and still end up with 2, but it just depends on what that fraction is. This is the process. It's the same as what we do with multiple angles, but one kind of variation in steps. Still going to solve this for sine of 1/2 x. So by doing that, solving for sine of 1/2 x, we'd have like 3 over 2 radical 3, right? Now we don't know that off the unit circle, but it makes sense to do this. So I get 3 radical 3 over 2 times 3. So what's that going to give me? Radical 3 over 2. So again, we're asking the question, when is the sine of x over 2 equal to root 3 over 2. Okay? So let's just go back to the same thing we did in the last question. When assign radical 3 over 2, pi over 3 and 2 pi over 3, good. Okay, but now what did we just solve for? What was the argument? X over 2. Okay, and just like the last one, when you're doing these multiple angle type questions, even if that angle is a fraction, you still add your period. So 2 pi k and 2 pi k. Okay. Now, what does that imply that x would be? What would I need to do to solve this for x? Multiply by 2. So x is going to be 2 pi over 3 plus 4 pi k. This one here is going to be pi over 3. No, sorry. 4 pi over 3. Messed that up. Multiplying by 2, right? Plus then 4 pi k. Okay. Now, when your n value was an integer, okay, and our n value here is this 1/2, right? When cursor froze. All right. So that 1/2 there is your n value. Well, the k that we were using was 0, 1, 2, 3, 4, all the way up to n minus 1, right? Well, now if we use fractions for n, it's kind of weird because k's got to be an integer, right? Okay, well, I can't take n and let it be a fraction then, because then the n minus 1 is not going to be an integer, so we can't maybe use that, okay? Or I guess not use it in the fashion that we've already used it in the last question. Usually what they're going to do here with these types of questions is give you the interval that they want you to solve your answer for, okay? So let's say that they're looking for answers just between 0, say solutions 0 to 2 pi, okay? Then all you do is you say, okay, we're still going to let k be an integer, but we just don't know where it's going to stop. We're going to start at 0, plug that in, evaluate. Match that answer back up to 0 to 2 pi. Then we're going to go to the next k value of 1. Plug that in, evaluate. Match that back up to the interval 0 to 2 pi. And I keep doing that, keep letting k grow from 0 to 1 to 2 to 3 until I find a solution that is outside the interval 0 to 2 pi, and then I stop with the k values. Does that make sense? Okay. So I think in this one it actually happens pretty quickly. If I let k be 0, okay, so if k equals 0, this provides, that's going to go away, right? So it just gives me x to be 2 pi over 3. Okay. Now if k equals, and that's in this interval, right? If k equals 1, okay, that's going to give me x to be, so this would be, over 3. This would be 12 pi over 3, right? So it gives me 14 pi over 3. Is that inside this interval? Nope. So that's not a solution. The only solution that I use, that I get from this, is when k was 0 at 2 pi over 3 being my x-value. Okay? Now, if that's the case, then for that bottom red equation, you're going to use the same k's. Okay? So I only need to use k equals 0 here on the bottom. So if k equals 0, then x ends up being 4 pi over 3. Okay, where you obviously see then if k was 1, because this was larger than that, and you're still adding 12 pi over 3, then this k equals 1. That number for x is going to be larger than 14 pi over 3, isn't it? So again, if it's larger than 14 pi over 3, it's still outside this interval. So whatever that ends up being, I think it's like 26 pi over 3 or something like that. That's outside of 0 to 2 pi. Okay? Now, what if that interval was different? What if the question said, find answers between 0 and 6 pi? Do I then keep that answer? Because 6 pi, and this might be a way of doing this, 6 pi is the same thing as 18 pi over 3, isn't it? Is 14 pi over 3 less than that? Yep. So then I try k equals 2. If k is 2, okay, so now I have 24 pi over 3 right here, right? Plus 2 will be 26 pi over 3. Do I use 26 pi over 3? No, it's bigger than that one. So can't use k equals 2. I would just use k equals 0 and k equals 1. And then use k equals 1 in that bottom one as well. Is that okay? So you don't really know how many k's you're going to use, kind of like you did with multiple names. Okay? And again, you guys can see this. I'll just graph. Where did Desmos go? There you go. Just graph the sine of x in square root of 3 over 2 first. Okay, and there you see you got two solutions in that interval. Okay, but if I start to look at x over 2 or something like that, okay, now you see, and let me actually put sine of x in here as well. Do you see how the green curve is taking the purple one and stretching it out? Okay, so we don't get maybe all the same solutions. Okay, we still get two solutions, right? Okay, if this was sine of 1x equals radical 3 over 2, we would have two solutions. But in this case, obviously they're different, and the two solutions come then from these two ideas. Okay, every once in a while, just depending on what that number is. Like I said, if you have initially, if we're looking at like a sine of 1x or something, you might have like 3 solutions or 4 solutions, but then when you change that fraction, it might pull some of those solutions outside your interval, so maybe you only have 2 or 1 or something like that. Okay, but generally speaking, with these, you'll probably have either equal or less solutions than what you would normally have with just 1x in there.
For the last two solutions that we get, would we do plus 4 pi k or would we do plus 2 pi k?
You would still do plus 2 pi k.
Is it always going to be plus 2 pi k?
Let's see here. Let's talk about that one. Well, let's do this real quick. You guys have any, before we do, because this question will run us through the end of the period if we just start on it right now. Do you guys have any questions about anything that's kind of stumping you? I know we've done a lot. Chapter 7 was kind of a big chapter. Yeah. All right, so we can use identities to help us solve trigonometric equations. Using a Pythagorean theorem, we see the equation sine x plus sine squared x plus cosine squared x equals 1 is equivalent to the basic equation. Okay, so what they're asking here is if we start, let me zoom in. If we start with this thing here on the left-hand side, okay, do we recognize that sine squared x plus cosine squared x equals 1? Okay, so, and they're taking a little bit of a liberty here by saying, okay, change that to 1. So you've got sine of x plus 1 is then equal to the 1 over here. And then if I wanted to solve the equation, then isolate sine of x, I would subtract 1 from both sides. And that's where I'm getting that sine of x equals 0 there. And then it says whose solutions are pi k for any integer. All right, so if I ask you on the unit circle, where is the y value equal to 0? Because that's what this is saying, where is sine equal to 0? It is there at 0 and pi, right? So we would say, usually what we've been doing is saying 0 plus 2 pi k and pi plus 2 pi k, right? Where k could be any integer. Well, let's just think about this. And I'm not going to ask you to do this tomorrow, but it is good to think about. If I let k be 1, 2, 3, 4 through here, okay, if it's 1, it'd be 2 pi k, or sorry, 2 pi. If it was 2, it'd be 4 pi. If it was 3, it'd be 6 pi, right? So that's giving me all my even multiples of pi. And here, if I let it be 0, I get pi. If I let it be 1, I get 3 pi. If I let it be 2, I get 5 pi. And so that's giving me all my odds, right? So an easier way of writing all of these, okay, would just be, if I look at them as a group, it'd be pi, 2 pi, 3 pi, 4 pi, 5 pi. We can even get 0. We can get negative pi. So that as a group, they're saying is just pi times k as an equation, because now you can just take k to be any number and you should be able to produce those. Does that kind of make sense? It's good to think about. It's good to recognize. A lot of higher level math courses are going to say, that's something that we need to know or be able to recognize and identify. But I'm not going to. If you got 0 plus 2 pi k and pi plus 2 pi k tomorrow on a question like that, that's fine. That makes sense. You don't need to write any simpler equations than that. Question 2. Says, using a double angle formula, we see that the equation sine of x plus sine of 2x is equal to 0 is equivalent to, okay, so sine of x can't change, but sine of 2x is that 2 sine x cosine x formula. Okay, so that's what we're looking, and you see it, that's what is put in that box there. Okay, so if we've got a sine of x plus 2 sine of x cosine of x, and several people have asked about things like this throughout this assignment. What do we do next? Well, this is one individual term, and this is one individual term. What do they have in common? Sine x. So take that sine x out, and what I'd be left with then is a 1 there, plus then 2 cosine x is equal to 0. And I think then, yeah. So solving the two basic equations, you get sine of x equals 0, which would be that one right there. And then the other one would be 1 plus 2 cosine x equals 0, or 2 cosine x plus 1 equals 0. So they're just asking you to go that far, not going any further, just seeing what those two factors then are of that original equation. So they're just trying to build you those processes that maybe we're going to use in questions maybe 3 and 4 and 5. Does that help? Any others you guys want to quickly maybe talk about or think about it? And throughout the day, guys, if if you're going over something that doesn't make sense, shoot me an email, come see me. Usually open during Wildcat time.